Okay, here's one of our objective functions problems again. I'm going to go straight to the question. How many of each type of worker should be hired to maximize the company's profits? And here's what I think you need to recognize. It's talking about profits, and so that's what's going to have to be in the objective function. So I'm going to use P, and it's talking about how many of each type of worker. So we're not going to focus on the money, we're not going to focus on the cost like we typically do. We're going to be focusing in our objective function on the workers. So it says experienced workers produce 1.5 times more profit than inexperienced workers. Okay? So we'll call our experienced workers X, and we'll call our inexperienced workers Y. And it says experienced workers produce 1.5 times more profit. So our objective function can be 1.5x plus y. Does that make sense? I hope that feels logical for you. So now we're ready to write our other equations so that we can plot them on Desmos and then evaluate what our vertices are from that. So it says that the department store is going to hire a total of 24. So we've got x plus y is going to be, well, it says up to. So it's got to be less than or equal to 24. So that's one of the equations we can graph. Looks like they're going to pay the experienced workers $20 an hour and the inexperienced workers $15 an hour. Do you see that? But they're not going to pay any more than a total of $400 per hour. So we can write an equation for that as well. 20x plus 15y is going to be less than or equal to 400. Okay, and obviously y is greater than or equal to 0. And x is greater than or equal to 0. So let's go to Desmos and get this all plotted and see what we can come up with. All right, so we know 20x plus 15y is less than or equal to 400. All right, and then we know our next equation, get another equation here. Our next equation is x plus y. X plus y is less than or equal to 24 workers, okay? And then we can add our x is greater than or equal to 0, and y is greater than or equal to 0, and it looks like we've got what we need here. So let's see here. We need to make this a little bit smaller here so we can actually see what's going on. Just keep zooming in here. All right, so we're getting some visuals here now on what we need. Okay, so this is a little bit harder to see exactly what's going on, but notice that both of these say less than. The top two equations both are less than, which means that it's going to be the shaded part below. So it's all of the portions that are shaded in the first quadrant, okay? So another thing I want you, well, here, let me just click on this. This is obviously going to be our first vertex. Let me zoom this in just a little bit more. And then our next, this is going to be one of our vertices here. Let's see if we can get that to record. Yep, 8, 16. And then over here, okay, see where that's double shaded? And it looks like this will be the other location. Yep, okay. So, oh, we don't need this one. But we did lose that one. Okay, so do you see there's our 4 vertices? Okay, that's our feasible region, the places that are all represented by those 4 equations. Okay, so now that you have those vertices, you can write those down, and then you can plug those in and answer the question from there. And I'm not going to talk you through the rest of it because you should be very familiar with the rest of these. But write your 4 vertices down, okay? So 4 vertices, and then you can plug them into the objective function and calculate which one is going to be the optimal situation.